The video disc, a product of the highest technology and engineering content requiring excellence from all affecting its production. We are all aware of the stringent requirements that NASA places on those who build satellites and manned space vehicles. The space shuttle is a stunning technical achievement, and yet a tiny amount of contaminant stopped the second launch of this 4.5 million pound craft. How small was that contaminant? It weighed less than 2 milligrams. Compared to the shuttle, it was 100 billion times smaller. But what does that have to do with video discs? In a video disc, a particle 1/10 billionth the size of the product will create a rejectable condition. Typically, it will launch the stylus 1,000 microns down the disc, 500 times the size of the stylus, or the equivalent of a 6-foot man jumping from one end to the other of our Rockville Road plant. Very small particles can and do cause large problems in all high-technology industry and present one of our greatest challenges in detecting and locating them. Let's take a look at a video disc closely. Here, under 1,000 powers of magnification, we can see the destroyed surface caused by the stylus riding over an embedded particle. To be able to see the individual grooves, we would have to magnify a disc 200 times, as shown in this photograph. But to be able to see the video information in the bottoms of the grooves, we would have to magnify the disc 10,000 times. You see, we deal in a microscopic world in the manufacture of the video disc. For perspective, if a disc were as thick as a 4-story building is tall, the grooves would only be a 1/2 inch wide, a 1/16 inch deep, and the information only as thick as 5 sheets of paper. On the same scale, the disc as thick as a 4-story building, it would be a mile in diameter. Using the Monument Circle for a hub, it would cover Indianapolis from East Street to West Street. Extremely accurate replication in plastic is what makes the video disc work. And that is why each operation in the manufacturing of video discs requires skill and attention to minute detail. Let's take a look at the visual inspection of a video disc. As soon as the transfer arm has gone in and another disc is being pressed, we can collect our sample. At the press, they will be examined for gross defects that would require immediate shutdown. From there, we can transport it to the inspection area, where we'll look for minute defects, things that require greater attention to detail. Here are some causes for immediate shutdown of a press. A cracked or chipped edge, as shown here, should be immediately communicated to the setup operator and his supervisor. Gross staining or scorched discs should also be communicated to pressing supervision and QA supervision. For the more minute details, we'll examine the disc closely under an inspection light. Here we'll look for such things as dents, stains, scratches, blisters or voids, and other defects found on discs. Once these defects have been found, they will be mapped. We'll go into this in a little detail. To map a defect, we would first locate it with our eye and then mark on the disc with a scribe its location. In the case of dents and voids, they may be circled, but stains which are large should be indicated with parallel lines. This mapping then is continued by placing the template on top of the fixture. On the template are the minutes of play. These should be recorded so that a fresh sample can be checked in playback evaluation to determine if these suspected defects will be cause for shutdown. Do not play a marked sample. Ultimately, all physical and electronic characteristics will be checked in accordance with specified procedures. To be proficient as a process inspector, we will require that you practice on the job the skills learned in this program. Here are a few of the tools that are used to check for warp, acceleration, and TIR, center and radius dimensions, gross warp, video profile, number of kicks, audio and video signal to noise, time-based stability, and defect gate. Each of these instruments will be gone into in detail in the next modules. RCA Select Division learning programs are divided into modules. This program is Module 1 of the Quality Inspection of Videodiscs. In these learning programs, each module addresses an objective. An objective is very simply something that we want you to be able to do in your job. In this first module, the objective is to be able to recognize
both the gross and minute visible defects that occur to video discs, and to be able to correctly handle a disc so as not to cause defects in its inspection. In addition to that, we want you to be aware of some of the basics of video disc technology and why it's important that you wear such things as hairnets, spit masks, and gloves. In the second module, you will see the methods used to physically inspect the video disc. Now, what we mean by physical inspection is simply that we will measure the profile of the disc, its thickness, its diameter, its both outer and inner diameters, in short, all of its physical characteristics. And in the last module, we will want to examine the electronic or playback characteristics of the disc. It's important for you as an inspector to realize that this is a consumer product and you bear a responsibility to maintain the very high quality of the video disc. You should see this in the discs that we produce.
To begin with, these are the parts of the video disc. The rim around the outer side is called the bead. It is essential that you keep in mind the nearly absolute precision of this product. Incorrect handling will cause damage. Again, the rim at the edge is the bead. It has been formed and trimmed to fit the caddy spine in a precision operation. The bead may be handled safely. This area is called the hump. It is a raised area at the center section of the disc. It too may be handled safely. On the hump you will see things which distinguish the A side from the B side. The A side usually corresponds to side 1 and the B side to side 2. Just at the center of the A side is the copyright statement shown here. Next on the A side are some wide circular marks. This is a barcode. Like the barcode used in grocery stores, a section of this code is read at the packing area to match discs with caddies. The barcode is put on the substrate in mastering, and in matrix this and all other information is transferred from the substrate ultimately to the stamper where it can be pressed to the disc. The copyright statement is engraved on the A plate, a piece of mold tooling. If you do not see barcodes on the same side as the copyright statement, you should suspect that the stampers and mold have been assembled incorrectly and should inform your technician, supervisor, or the press floor supervisor. Also on the hump of the A side, you will find the press run number, handwritten. Although difficult to read at times, it is an essential piece of information which must be copied accurately to your QC paperwork. This area, the one that reflects the colors. This is the signal area of the disc and really what our product is all about. All of the efforts of software review, mastering, matrix, chemical and physical lab, compounding and pressing are to make microscopic impressions inside grooves so small that 40 would fit on the thickness of a hair, up to 10,000 of them per inch. The impressions in the grooves are smaller than the frequency of white light, and that is what causes the light to break into all colors of the spectrum. As a process inspector, you will not only look for large features and defects, but also for the tiniest speck interrupting the pattern of colors. These defects must be identified because they could either damage a stylus or degrade the quality of the disc in the hands of the customers. You will not only check for such gross features as radius and thickness of the disc, but tiny specks like this one. At regular intervals, such as the 80th, 240th, and every 480th disc thereafter, the discs are played in the Performance Evaluation Test System, known as the PETS, and they represent a breed of automatic test equipment that is beyond state-of-the-art, much like the discs they are used to check. A specially calibrated PET styli is a very high cost to RCA, and this is another reason why that no gross defect should be played on a PET or any other piece of playback testing equipment. In addition to protecting the customer's video disc player and ensuring their continued viewing quality, you will provide essential information to the video disc setup operator in terms of defects that they can correct for, and when a press run will have to be shut down for found defects. Let's begin the handling of a video disc with how you handle yourself. Many people do not understand the vital part that cleanliness plays in the manufacturing of video discs. But if you comprehended the earlier segments of this module, you will be able to apply this learning to real applications. The best insurance we have of profitably manufacturing video discs is in our adherence to environmental specifications and procedures. The chemical analysis of video discs indicate that an average disc has about 0.6% contaminant, a higher purity than many prescription drugs. The air quality in the clean rooms, pet area, and presses exceeds surgical standards and approaches aerospace quality. It is because the surface of the disc that we are most concerned about dust particles or hair falling on them, for they would have a potentially disastrous result. By comparison, you see here a hair and the surface of a disc. The image has been magnified 1,200 times. Here you can see a tiny dust particle so small it would be barely visible, and yet to us it causes problems. As a process inspector, you will handle hundreds of discs a day. Some of them may be returned back to manufacturing for processing. The rest will undergo testing. If damaged by incorrect handling, your test results will be invalid. At the top of all people, or most of us anyway, is hair. And although we may be clean by human standards, we all collect dust and shed particles. For this reason, dust-tight hairnets are required in all disc manufacturing areas. These, however, should not be worn in other areas of the plant, where they too can collect dust. Instead, put them in a coat pocket or bag. When wearing the hairnet, it should be arranged in such a way to cover all of the hair, or otherwise it is no more than a useless decoration. Similarly, the disposable clean room gloves must be worn whenever collecting, preparing, or evaluating samples. Without them, particles and hair on the hands may fall onto a disc. Particle masks are worn in a manner covering the nose and mouth to avoid contamination of the surface of the disc by exhalation. Lab coats must be kept clean and should not be worn outside of the work area. Your efforts directed toward keeping yourself within specifications helps to ensure the continuing success of video disc operations. Once every precaution has been taken to prevent accidental damage to the disc, we may collect our samples and begin our visual inspection. Our first decision is to determine if our defect is random or pattern in occurrence. Both defects may represent shutdown conditions. Scratches, as shown here, may be either random or pattern in occurrence, depending on whether they occurred during the handling of the disc or if they are the result of a scratch stamper or a mechanical defect in the press. They will be pattern in the later case, which is the scratch which will occur in the same place on every disc. This scratch is a handling scratch, usually a very thin scratch. Handling scratches on stampers may appear to be the same to the eye. However, they will raise above the surface of the disc instead of being below. This scratch is generally caused by mechanical means and is called a process or press scratch. These scratches are generally wider than a handling scratch. Here we can see, under 1,000 powers of magnification, the trench dug in the ditch by this mechanical scratch. Another common defect is the dent. Here we see a pre-stamper breakage dent condition. Not all dents occur in a pattern of circles like this, but dents generally occur in the same place and should be circled and located in the mapping procedure to determine if there is a shutdown condition. Here you see a void. A void is caused when a bubble of entrapped gas collapses. Here you can see the same void at the normal viewing distance. Most disc defects simply appear as small black dots. Blisters are voids which did not collapse and may be caused by incorrect ram speed or incorrect humidity in the compound. Frequently, voids and blisters can be corrected for, and therefore this information should be communicated to the press floor supervisor and your technician. Here you see some fluid on the disc. Oil will cause a darkening of the surface of the disc. What has happened here is some hydraulic oil has leaked out of the video disc press. What we see is damage to the disc caused by press oil. Water spots are another typical fluid damage to the disc surface. Both press oil and water spots indicate conditions which are caused by malfunctions of equipment at the alpha press and must be reported immediately. Although they may not occur in exactly the same place on each disc, they would be classified as pattern because there will be evidence of these spots on every disc. Here you can see close up what water spots look like. This is a rejectable condition. Here you see what's called a radial stain. It radiates out from the center like a spoke. Radial stains are different from water spots and press oil. Most stains are also pattern defects. You can tell that there's a slightly different color to a stain than there would be in the case of oil or water. A more common kind of stain is what's called center staining. Here it radiates out from the center or hump area out into the play area. This defect is on the stamper. In this case, it is spread to the center play area and would be cause for a rejection. Pattern defects are always in the same place on every disc. Dents, stains, scratches, fluid spots, blisters, voids or uprisers may all occur in pattern. They should be mapped using the mapping procedure. Almost all defects will cause a defect in playback, which appears as a skip in both the soundtrack and visual portion of the scene. Uprisers, dents, scratches, and stains may cause bounce marks that we call chicken tracks. If these conditions are outside of the specified run limits, then it is called for a shutdown. There are different run limits for both random and pattern occurrences. Here you see a defect known as pulled coin, where the inner coin region of the stamper has begun to pull away from the mold. You can see it as a slight flattening of the circle just above the word proprietary. This region is a pulled coin and will eventually pull loose and cause compound to get under the stamper. Here you see a crack at the inner dimension that breaks further when the disc is flexed. In these cases, there is another problem which must be communicated to your supervision. This concludes the portion on handling and visible defects to the video disc. Please feel free to review any portion of this module if you have questions. When you feel confident in the information presented here, request the on-the-job training from your supervisor or technician. Quality Inspection of Videodiscs. Module number 2. The physical inspection of video discs. The methods for measuring the parts of a disc to determine if it is physically within specifications. The objectives for this program are to show you how to measure TIR, OD warp, acceleration, disc radius, bead hump thickness, and video profile. The second objective is to be able to check center hole diameter and dish warp. The importance of each inspection will be covered. To get accurate data, it is essential that all inspectors measure the same way. In this way, we can ensure the quality of the product. Test number 1, measuring total indicated runout, or TIR. TIR is how far off center the grooved area is. Circles are never perfectly centered, but if the signal area is more than the thickness of 3 sheets of paper off center, the picture will jerk. Here's how to measure TIR. Holding the disc by the edge, it is placed on the turntable. The spindle is slightly lifted and tapped down to ensure centering. Then the optical unit and the microsense unit are rotated into position and the turntable is turned on. You will now observe the lines marked on the display to the left. The space between each line equals 1 mil of TIR. Observe how many spaces are covered by the moving line and subtract the number of mils indicated on your tester for equipment error. Record the TIR on the QC inspection sheet. Once you have completed this operation, you will check for warp occurring on the outer dimension of the bead. This is OD warp. This affects primarily the bead area and is read with a microsense reader. Test number 2, OD warp. In this test, we will detect warp along the bead of the disc. This warp, if exaggerated, would look like this if seen from the edge, but really it is too small to be seen with the eye. However, it would cause the picture to skip through the affected area. To check for warp, push the button marked warp, and the digital reading that you see is the warp measurement. Enter the information on the QC inspection sheet. Having measured both TIR and warp, we may perform the third test, that of acceleration. After recording the warp measurement, we begin this third test. The steeper the slope of the warp, the greater will be the acceleration of the stylus. The warp measurement tells us how high the warp is, but 2 warps of the same height may cause different acceleration. The acceleration measurement tells us the profile of the warp and whether or not it would cause a skip. To test for acceleration, press the XL button, wait for the display to stabilize, and enter the information on the QC sheet. Now you may turn off the TIR warp and acceleration machine using the power switch and brake. Note that because this machine measures sensitive physical characteristics of the disc, do not slow down or stop the turntable with the use of the hand. Once it is stopped, turn the disc over and repeat the procedure exactly. Raising and gently tapping the center spindle, moving then the microsense unit and the optical units back into place, and turning the turntable back on. Then observe the line on the TV screen to the left. This will display the TIR of the disc. If the line was very hard to see, you may wish to use the slow speed mode of the turntable. Remember to subtract for the line width of the TIR measurement device. Having measured the TIR of the disc, the next operation would be to check for warp, done by pressing the warp button, and once the reading has stabilized, recording the information. Next, we would check for acceleration by pressing the acceleration button, and again, when the reading has stabilized, we'll record it. Test number 4 and number 5 are performed on the next fixture, the center hole diameter and disc radius. These measurements are important because if they are not right, the disc will not play in a consumer player. This is the center hole gauge. The two sections of the gauge are different in diameter by only the thickness of 2 sheets of paper. A good disc will pass over the first, but not over the second section. If the hole were too small, it would not clear the first rim. If the hole were too large, it would pass all the way over the second rim. Never force any measuring gauge. Having measured the center hole, we will next measure the radius of the video disc. On this gauge fixture, the measurement is always 5.9 blank inches. This gauge will give us the reading of the 100,000th of an inch of disc radius. The 2 blanks. Place the disc on the fixture and gently place the center hole plug into the fixture. Then, by rotating the disc, you may get the high and low radius measurements. In this case, we have 5.9 for the gauge itself. And to fill in the blanks, we can look at the gauge and see that we have 5.949 for our high measurement and 5.941 for our low measurement. Check these measurements against specification and record them. Test number 6, dish warp. This is a lack of flatness which affects the entire disc. Dish warp is measured using this tester, which uses the conductive disc and 2 pieces of metal to determine if the disc is warped above a tolerance. There is a reset button located directly below the LED display. By pressing the reset button, you can light the green LED, which is the mode in which you wish to begin starting the test. As you can see, the disc is placed on the table of the test device, and then we press the reset button. Now the bar is drawn gently across the disc, and as you can see in this example, we have a red LED indication telling us that this disc is warped out of tolerance. This information will have to be communicated to the setup operator. Dish warp frequently is a condition which can be corrected by changing press parameters. As you can see here, we'll test the other side of the disc. And interestingly enough, after resetting, we see that the disc shows warp on only one side. This is typical. Test number 7, bead hump thickness and video profile. These are important because if wrong, the disc will not work with the caddy. In this test, we will measure the bead and hump and video profile of the video disc. First, we reset the indicator meter by pressing the button on the side. Next, we raise the measuring plunger using the black button on the cable. As you see, the meter was zeroed and then raised. Then we place the disc under the indicator plunger. A video disc is divided into 8 sections. These sections contain video information. You can use them, though, to keep track of which quadrant of the disc you are measuring. We wish to measure the disc at 4 equally spaced points of bead, and then use a calculator to determine the average height of the bead from the floor of the test fixture. This measurement is precise to the 10,000th of an inch, 4 zeros to the left of the decimal point. Any instrument which reads to this tolerance is extremely sensitive and must be handled with care. Never force a video disc under the measuring probe. Once you have determined the average bead height, record the information on the inspection sheet. With the check of the hump, the bead completed, we may now check for the hump height. This is done by relocating the video disc in such a way that we will be reading the hump, or central raised area of the disc. We slide the turntable in and relocate the measuring probe. Again, we will take 4 equally spaced measurements and, using the calculator, average them to determine the average hump height. Once we have determined the average height of the hump, we will write the results on our sheet. The final test used on this fixture is that of the video profile. The video profile is a measurement at 2 points in the signal area of the disc. The signal area has a lower height from both the bead and hump. Once again, we would use the markings on the disc to determine our 4-point reading, just as though we were dividing a circle into 4 pieces. To measure video profile, you just locate the probe inside the bead area, and again, measure the 4 quadrants of the disc. This will be to determine the average thin area of the disc, or low reading. Once you have determined the low video profile, relocate the probe to just outside the hump area as shown here, and again take your 4 readings. These 7 tests complete the physical inspection of video disc. Feel free to review any portion of this videotape, and when you feel confident in the performance of these tests, request the on-the-job training from your supervisor or technician. In the on-the-job training, you will learn the specification and sorting limits which apply to the physical inspection of the video disc. Quality Inspection of Video Discs. Module number 3, Playback Testing. The objectives of this module are to provide you with the information necessary to be able to operate several pieces of test equipment: the kick counter, the defect gate counter, the time-based stability tester, all of which use the Ruggedized player. Our second objective is to be able to operate the ACNR and VSNR test devices. These are tests which are to detect defects which you would be able to see or hear. They will detract from pleasurable viewing, frequently severe enough to cause a disc to be returned. In the previous modules, you have seen tests which identify obvious and visible problems, including those problems with size and shape. In this section, we will test the true product, the part of it that our customers will see. Our standard should produce very high quality programs. In these scenes, we see our specifications in action, what every disc could look like. The high video signal-to-noise ratio provides for a sharp, bright, clear picture. The low defect gate count makes for a clean picture without black dots, white spots, or unstable color. The stable time base makes the picture move only if it's supposed to. The high audio carrier to noise gives a sharp, high-fidelity sound and good separation in stereo. And the low kicks mean that there will be no skips in critical portions of the program. Nothing that you will do as a process inspector is as important as these tests. Here are some examples of defects which have caused field returns. Skips are the most frequent complaint. Here is a letter received from a customer in 1982. Yes, skips can be very irritating, but you may be the solution to them and other sample defects by keeping us within specifications and aiding in the avoidance of pattern defects. Your communication pinpoints where our engineers will look to improve product quality. Here we see defect gate. Defect gate causes small white dots or black spots to appear on the screen. These may have a sparkly or colored appearance. And here you can see poor time-based stability, causing the picture to wiggle or move, particularly visible on vertical lines. But not all people feel negatively about our product. Only 3% of the discs produced have been returned to the factory, and most of those defects due to damage in handling or contamination. However, about 4 press runs per month are passed that should have been failed. The videotape that you are now viewing could not pass the quality standards for video discs. Often, though, consistency, even if consistently inferior, may be seen as better quality. Only lubricated samples may be tested during playback. Unlubricated discs will wear out styli and give false test results. The areas of suspected defects that were mapped in visual inspection will be of primary interest, located by minutes of play. The Ruggedized player is the beginning of all but the ACNR and VSNR testing. In this section, you will learn how to operate it. The player used for video disc testing does not require the use of a caddy and makes testing quicker. This is how it's used. Take a loop disc and place it on the spindle. Check that the power is on, indicated by the red power button. Then push the button for turntable on. Make sure that the lock switch is in the open position, and then draw the arm forward into the play area, watching the minute display. Lock your arm and the minute display will flash. This says that the player is in a pause mode. If you are ready to begin the test, press the pause button and then release it. This will cause the stylus to come down on the disc and begin to play and display the picture on the television set. Also, you will see the display of the actual minutes of play. The arm can be moved forward and backwards using the fast or the scan buttons. The fast reverse button rapidly moves the arm in reverse playtime. The fast forward button moves the arm forward quickly, further into the program. The fast mode, both forward and reverse, eliminate any picture from the screen. When you wish to view the picture, you will use the scan forward or reverse. These buttons operate the same as the fast mode, but instead speeds up the picture so that you can scan through the program to the area of defect you wish to view. To continue your test on the other side of the disc, turn the turntable off, and when it is stopped, carefully flip the disc over and repeat the operation. Now let's use the Ruggedized player to test for kicks. This is the kick test station. You start by loading your disc and turning the turntable on. The kick test station is used to count how many times the player has to kick to get out of a serious defect area. These will be displayed on the TV screen as skips, though some too short to view. The test box on the left displays, in the upper right-hand corner, minutes of play of the disc. It indicates the number of kicks occurring in 1 minute time on the upper left, and in the lower left, the number of thousands of micro defects occurring in 1 minute of playtime. You start by resetting the test box and watching the player play through the area of suspected defect. If a defect occurs that causes the player to kick the stylus, it will be registered here. This has just registered a defect area. It has caused it to kick twice. When it plays through minute 17 and starts into minute 18, it will automatically print out on the tape below the number of kicks and the number of micro defects registered in that minute. The 04 represents 4,000 micro defects occurring. Included with each Ruggedized player is another test device. This is the bad stylus indicator test box. As long as the stylus used in the test is in good condition, the BSI test light will remain out. But if the stylus is beginning to wear or in need of cleaning by the technician, the BSI test box light will light continually. At that point, you should indicate the problem to the quality assurance technician, who will clean or replace the stylus as necessary. Our test has now clicked over to minute 18. When that happens, all displays on the kick counter test box will zero themselves and start counting again. That completes the operation of the kick counter. Kicks should be compared against specifications. The time-based stability test is next. It again uses a ruggedized player like the kick counter. First, turn on the turntable after loading the disc and move the arm inside to the area to be tested. Then, lock the turntable arm into position and press pause, beginning the time-based stability test. On the time-based stability monitor, there is a display of 3 vertical lines. These lines are for reference purposes only. If there is a time-based stability defect, the lines or the picture behind them will become wavy. When a time-based stability defect has been determined, the information must be entered on the Hewlett-Packard 9825 calculator shown here. The program minute must be noted and 1 sample test entered. The sampling of 1 represents 1.6 minutes during which the test takes place. At the conclusion of the 1.6 minutes, if there is a printout, the QC technician or the QC supervisor must be notified that there is a disc that has a time-based stability defect. The press floor supervisor must also be contacted. The printout will let us know whether or not we are within limits.
If the playtime finishes and there is no printout, then we know that the test has been concluded. Once the test has been completed, take the disc off of the turntable, unlock the turntable arm, and turn the turntable off. You may then return the arm to its resting position towards the back of the ruggedized player. Wait until the disc comes to a complete stop, then remove the disc for either testing the other side or proceeding to the next workstation. Now let us see the method used for testing video discs for defect gate. Again, we will use a ruggedized player. Place the disc on the turntable, turn the turntable on, and move the arm to the inside, locking it into position. We will press the pause button to begin the test. We will scan through the disc and test 5-minute increments to determine if there is a defect gate problem visible. Defect gate might be noted by a snowy picture, somewhat like poor reception from a television station. When the position of suspected defect gate is reached, press the reset switch. The count takes exactly 10 seconds. After 10 seconds reading has been taken, compare it with the specifications and record it. Once you have taken your readings, unlock the arm, turn the power off on the turntable, place the arm completely against the backstop, and when the turntable stops completely, take the disc off the turntable and either proceed with testing or on to the next test station. Now we will see the test used to check for audio carrier to noise and video signal to noise ratios. Begin by powering the system up if it is not already on. Then turn on the control module. The system should now display System Ready. If it did not display System Ready, you would just push the return button. When System Ready is displayed, type in the letters EXE and press return. When the display reads outside, Y, or in, you know that the system is running and ready to begin the test. Begin the test by loading the disc on the spindle, centering and tapping the spindle, and then push the play button. Now the arm will automatically begin to move over. To take an outside measurement, press the Y on the control module typewriter keypad. As soon as the stylus is set down, the monitor will display black field, and then push the return button. The first reading will be taken at 716 kilohertz, represented as KHZ in the display. Also, a bell curve will display on the spectrum analyzer in the test rack. This indicates that the test is in progress. When the 716 kilohertz test is complete, the tester will automatically begin to take another reading at 905 kilohertz. These two readings make up the outside audio carrier to noise measurement. When both readings have been automatically completed, they will be printed out on a tape. You may then take the tape and compare it to the written specifications for acceptance. After the ACNR test is complete, our next test is VSNR. Use the play button to move the arm to the inside of the play area. Check the monitor to see that you are near the end of the program, and then begin to perform the VSNR test. This test uses the upper spectrum analyzer. The two dials on the lower right are used to alter peak-to-peak variation in the center of the display. By moving the pedestal level button shown here, the display area can be moved up or down. The pedestal area must be set level with the two signal areas on each side. such that a straight line is established. As you see here, it can be raised up or down, but should be level with the other two. That's the pedestal level button. You want them to match also the height. As you can see, the line has high and low places. By adjusting the two knobs on the far right hand side, these heights can be raised or lowered such that the noise in the center matches the signal on each side. When the readings are matched, we can take our reading. The VSNR readings use the noise generator below and the spectrum analyzer above. This is the pedestal control, as it raises or lowers the reference noise signal. To perform the test properly, balance the pedestal level so that it matches as close as possible the signal levels on either side of the display. This represents the noise, and the outside represents the signal. Here the noise, and there the signal. Match them as close as possible in level, and then by adjusting these, the noise strength dials, we can increase the amount of noise or decrease the amount of noise. You see here it is increased, and it can be decreased to be a flat line. We wish to exactly match the outside signals to the inside noise by adjusting the dials. When we have it exactly matched so that they look the same, we now have a correct reading for VSNR that is found simply by adding the value which is found on these strength dials here. 40 plus the value on the other knob, which is 9. 40 and 9 for 49 dB of VSNR. After completing the VSNR test, we will want to test the ACNR readings at the inside of the disc. So we return to the turntable. Again, advance the arm by pushing the play button until we reach the point right at the end of the program where we have black field with no sound. At that time, push the in button on the keypad of the controller and then press the return. This will begin to take the 716 kilohertz reading as indicated by the bell curve on the lower spectrum analyzer. When that is complete, the system will automatically begin to test for 905 kilohertz. It performs the same measurements as was performed for the outside ACNR. When the system automatically completes its measurements, it will again print out the results on the paper tape. When the test is complete, there's the paper tape. When the test is complete, simply press the stop button on the turntable. The arm will automatically return to its start position, and the turntable will automatically turn off, and the disc may be removed for other testing. This concludes Module 3 of the Quality Inspection of Video Discs. Your rapid and accurate performance of these tests plays a vital role in video disc manufacturing, making consistently high-quality programming available to our customers and assuring their quality viewing. Feel free to review any portion of this module, and when you feel confident in the performance of these tests, request the OJT from your supervisor or technician. In the on-the-job training, you will learn the limits of playback testing and the sorting limits and specifications which apply.